Are you talking about the Frohman bracket?
I just want to clarify one point, okay? Take any three manifold, you take the Kaufman bracket Skane module of the three manifold at -1, that is a ring. And then you mod out by its radical, and that is the coordinate ring of the SL2C character variety of the fundamental group of the three manifold. Okay? So I guess I wasn't explicit enough about that. So where we're headed is we want to find invariance of elements of the mapping class group derived from this algebra. That's where we're headed. And the way we're going to go about that, you see, the algebra is hard. If you have two framed links and you multiply one by the other, and there are n crossings, then to compute the product, there are 2 to the n terms in the product. So multiplication in the algebra has exponential complexity. And you know, with most algebras, they're just like these abstractly defined things, and you can't really figure out what's going on. And so what you do is you map that algebra to matrices. And the thing about matrices is you can know everything about a matrix in polynomial time. And so the way you study algebras is by taking homomorphisms from the algebra to matrices. And so I'm just going to back off. And the stuff I'm going to say, I might be, for people who do this kind of thing, I might put you to sleep a little bit. But I find that a lot of people who work in topology are unaware of this stuff. So that's where I'm going to start. So A is just going to be an associative algebra with unit. And you want the algebra to be fairly nice. And for non-commutative algebras, there is a concept that generalizes being an integral domain, and that's being prime. And we say A is prime if, whenever you have A and B in A, if it is the case that for every R in A, ARB equals 0, that implies A equals 0 or B equals 0. Now, in the case of a commutative ring, of course, you can factor R to the outside, and then that is just a statement that it's an integral domain. But you see, like, n by n matrices over the complex numbers, they have dimension n squared. And the basis is given by matrices Eij that has 0 everywhere but the Ij entry, where it's 1. And then multiplication is really easy. To multiply Eij times Ekl, well, most of the time it's 0 unless k equals j, and then if not, then it's IL. It's got 0 divisors. Okay, and yet it's the nicest non-commutative ring there is. This definition, it turns out that matrices are a prime algebra, because what I can always do, of course, is insert Ij KL. I just insert JK in here, and then the product's non-zero. And so this is just a slight loosening of no 0 divisors so that most nice non-commutative rings can be prime. Okay. So then because it's non-commutative, you can have left ideals and right ideals and two-sided ideals, right? And does everybody know what an ideal is? Yes. Okay. A two-sided ideal I is prime if given A and B in A, if for every R, A, R, B is an element of I, that implies A is an element of I or B is an element of I. And of course, if you take the quotient by a prime ideal, you get a prime ring. Okay. And if you're used to thinking about algebraic geometry, when you're given your commutative algebra, then the geometric objects associated with that commutative algebra are the ideals. And then if you want them to be nice, then they're prime ideals. And if you just want to talk about points, then you talk about maximal ideals. And then you can topologize the ideals with the Zariski topology, and you have a topological space. Okay. So then, is affine if it is finitely generated. And that gives you a certain amount of compactness for your associated topological space. And this just means it's a quotient of polynomials in non-commuting variables. Okay. And now, of course, the center of A is all Z in A, so that for every R in A, RZ equals ZR. Great. Now, if your algebra is prime, then its center is an integral domain. And what you can do is you can then form the non-zero elements of the center as a multiplicatively closed subset. And now S inverse of A is an algebra over the field S inverse of Z of A. Okay. A division ring is an associative algebra so that every non-zero element has an inverse. Okay. And now this is one of the few really deep theorems of structural ring theory from the 1970s. This is Posners Theorem that says if A is prime and has finite rank over its center, there exists a division algebra, a division algebra, so that S inverse A is Mn of D. So once you localize the algebra, it becomes matrices over a division algebra. Now, when your base field is algebraically closed, there is a severe lack of division algebras over it. So if you have an algebraically closed field, it is the only division algebra over its field. Yes?
What do you mean by A is prime?
The algebra A.
So
If A is prime, a prime algebra, and it has finite rank over its center, which would be Z of A.
so prime okay, so we got what a prime ideal is. What's a prime algebra?
A prime algebra, okay, so prime algebra just means that if for every R, ARB is 0, then A equals 0 or B equals 0. So it's a mild extension of integral domain. And in the case of commutative rings, it just means integral domain. Okay. So now what you can always, by the way, division algebras, their dimension is always a square, right? And you can always then, what you can do is you can complete. There's a splitting field, and you can extend coefficients by tensoring with a field. So this becomes some matrix algebra over a field, and E is D, tensor. Boy, I'm making a mess of this. Let me just do an example. How about that? Here's a division algebra, the quaternions, right? And you know that it's a four-dimensional vector space over the real numbers, and it has as a basis I, j, k, and 1. And now, if I just extend coefficients, so multiply by the complex numbers, what I get are 2 by 2 matrices over the complex numbers. And so let me just get to the point. A embeds in a matrix algebra over a field as an order. And what it means to be an order is if I call this theta, if I take theta of A and then multiply by all elements of the center of MNK, then I get MNK. What it says is that a prime algebra that has finite rank over its center is almost a matrix ring. Okay? That's what it says. And because of that, the representation theory of these algebras is really nice. Okay? And so now I have to tell you what a representation is. Okay. So a representation of an algebra A is just a homomorphism from A into a matrix ring. Is that okay? That's all I mean. Now, another way of seeing that is, of course, this turns Cn is a left A module because, of course, matrices act on column vectors. Okay? And now rho is irreducible if, and one thing they'll say is it has no non-trivial invariant subspaces. Okay, so if I have a linear subspace of Cn that is stabilized by the image of rho, then it's either 0 or the whole space. Or another way to say it is Cn is strongly cyclic. And a module is strongly cyclic if any non-zero element of the module is a cyclic generator. But really, this is what you should think. Rho is onto So in fact, an irreducible representation is just a homomorphism from the algebra to a matrix ring that's onto. So you take a quotient of your algebra by an ideal, and you get a matrix ring. Okay. So now, if A is commutative, the only irreducible representations are one-dimensional. And so here in the case of a commutative ring, now we're just talking about a homomorphism to the complex numbers. And now if C is affine and an integral domain, I guess, but I think I just need affine, then the homomorphisms rho can be placed in one-to-one correspondence with the kernel. So there's only one homomorphism that has the same kernel. C is just a commutative. Oh, C is a commutative ring. I'm sorry. Am I making sense? Okay. You can see I'm almost as uncomfortable with algebra as you are. Okay. And so then what you do to get a geometric object is you define the maximal spectrum of C to be the set of all M in C, a maximal ideal. And then by the weak Nullstellensatz, that just corresponds to the irreducible representations of the algebra. And now you give it the Zariski topology. And so then you define if A is an element of C, V sub A is the set of all maximal ideals such that A is not an element of that ideal. So basically, whenever you have a ring, a commutative ring, you've got a geometric object, which is the maximal spectrum of that commutative ring. And you know, like in the case of SL2C character varieties, basically each maximal ideal in this ring corresponds to a trace equivalence class of representations of the underlying surface, fundamental group of the underlying surface. So then this leads us to noncommutative geometry. And what is noncommutative geometry? Well, you're going to treat your ring as a geometric object, and the idea is that the points of that geometric object are its irreducible representations. And so the points of an algebra A are its irreducible representations. So that just means onto homomorphisms from the algebra onto n by n matrices. You're finding a bunch of matrices that act just like elements of the algebra. That's what you're doing. Well, I want to remind you guys of the Skolem-Nether theorem. And what it says is every automorphism of MNC is inner. Okay? So now, suppose I have a representation from A into MNC, and the kernel of rho is the prime ideal I1, and say a representation rho prime, well, how about call that rho 1, rho 2, from A into MNC, and now the kernel of rho 2 is I2. And now suppose they're equivalent representations. So what I've got is I've got A, and then A mod I1, which is a copy of Mn of C, and there's row 1. And I've got A, and I've got row 2 to A mod I2, which is Mn of C. And then saying that these are equivalent representations means that if I go from here to there, I'm defining an automorphism, theta, from MNC to MNC, which is an automorphism. But then by the Nether-Skolem theorem, that means that I can realize theta as conjugation by some invertible matrix. So there's some L in Mn of C, so that when I apply theta to some matrix, it's L inverse ML.
Sorry, what is the notion of equivalence or representation?
That there would be an intertwiner from one to the other that's an isomorphism. So you can either intertwiner from one module to the other that's an automorphism. But what I'm going to tell you is that because of this, it turns out that equivalence is the same thing that you expect. Basically, the weak Nullstellensatz is still true, that two representations are equivalent if and only if they have the same kernel. And so you don't actually have to worry about it. That's the point. Okay. Well, so now, suppose rho goes from my algebra to Mn of C, and it's irreducible, which just means onto. Well, that tells me that it takes the center of A into the center of n by n matrices. But the center of n by n matrices is just complex multiples of the identity. And so then there exists a function from the center to the complex numbers, so that if I apply rho to an element of the center, then I'm getting chi of rho applied to Z times the identity map. And that is the central character of the representation. Okay. And now, what you'd like is you'd like to be able to classify irreducible representations of your algebra by their central character. That's what you want. And now when you think about it, that seems really hard, right? Because you might have different prime ideals in the algebra that intersect the center in the same ideal, right? So your algebra had better be pretty nice for this to happen. And that's what Amaya Algebras are all about. So these first appeared as maximally central simple algebras in 1956 in Amaya's PhD dissertation. And so A is Amaya if 1, A is a finite rank projective module over its center, And then there's a map from A tensor A op into central linear automorphisms of A. And what it does is if I have alpha tensor beta and I want to apply it to gamma, I just take alpha gamma beta like this. And then you require that to be an isomorphism. And those two conditions imply that your algebra is Amaya. And if you read like physics papers, like in the last 10 years, Amaya algebras have become really important in the physical literature. And more or less, this is the reason here. So if A is Amaya, you have ideals of A, and you have ideals of the center of A, and the map that sends I to I intersected with the center of A is a one-to-one correspondence. So in fact, basically, there's one irreducible representation of an Amaya algebra for each point in the variety corresponding to its center. Okay. And if you want to do quantum mechanics, that's a really, really important thing. You see, all you can do is make classical measurements, right? Any measurement, any experiment you take, you're not, like when you're doing measurements, you're not measuring an operator. You're measuring and you're getting a number. And then physicists take those numbers and they turn them into matrices and they do computations with the matrices and then they get physically appropriate answers. And so that they're working in an Amaya algebra says they can take their physical measurements, which determines a point in there, and then there's a unique choice of matrices to work with over here where they do their computations. All right. And now you know that, so yeah, yes.
Are these two things equivalent? The Amaya having a common ideal?
No, there are algebras. Like for instance, if the algebra was free over the center, then it happens a lot of the time. Okay. But this is, and this is a really, really strong condition, right? It's a really, so you can't hope for it. But then there's a theorem, and this is of Michael Artin and Claudio Procesi, that says that if A is prime, has finite rank over its center, prime, and finite rank over its center, then there exists C, an element of A, actually in the center of A, so that if you let S be just the powers of C, then S inverse of A is Amaya. And so you can always localize a reasonable algebra. So what does localization do? You're declaring that a bunch of elements of your algebra, well, of the center of your algebra, are invertible. If a prime ideal contains a unit, it's everything. And so what you're doing is you're destroying a bunch of prime ideals, which means you're destroying a bunch of points in your geometric object. And localization is the algebraic equivalent of cutting a manifold open along a submanifold. That's what it is. Okay, you're cutting the geometric object open when you localize. And so, more or less, when you think about it, you can always cut a manifold down to balls. Well, you can always cut an algebra that's reasonably behaved down to being as Amaya. So these are the sort of primitive pieces. And then there's sort of an obvious thing. If I1 and I2 are prime, and S intersect I1 is empty, so you're not destroying I1 or I2. If S inverse of I1 equals S inverse of I2, that implies I1 equals I2. So when you localize to make it as Amaya, that uniqueness you get actually still holds in the original algebra. And so the idea is to localize so that the remaining points of your algebra are uniquely determined by points of the center. And what's amazing is that this theorem didn't appear in the literature until Monday, right? So this is, and you know, I asked a lot of people, you know, because this had to have been done, and you know, their response is, well, it's a trivial extension of what's in the literature, but in fact, it didn't appear in the literature. And this, I call this the Unicity Theorem, and this is in a paper by Frohman, Kanya, Bartoshinsky, and Lay that went up on the archive on Monday. Okay. If A is prime, has finite rank over its center, there exists VC, a Zariski open subset of the maximal spectrum of the center of A, so that so that, well, here's irreducible representations of A, and here is the maximal spectrum of the center of A, and given a irreducible representation, of course, then you have the central character, and then you send it to the kernel of the central character. And this map is onto. So there's an irreducible representation of the algebra for every point of the variety associated with the center, and it is 1-to-1 over VC, which means that as long as you tear out this essentially measure zero set of bad points of that variety, then there is a unique irreducible representation corresponding to the point of the variety. And all the reps, irreducible reps over VC have the same dimension. And that dimension is the dimension of the vector space where now S is going to be just the non-zero elements of the center. That dimension is the dimension of the algebra as a vector space. So it's the dimension of S inverse of A as a vector space over the function field of the variety associated with the center.
What is S here?
S is z of A minus 0. So I'm just forming, that's the function field of the variety of center. So it turns out that when you have an algebra like this, it has a very reasonable character variety. And in fact, the character variety is just the character variety of the center. And then most of the time, there's a unique irreducible representation of the algebra corresponding to the point in the center.
So can you say anything about what this bad set that you have to throw in?
I can. There are lots of ways of getting at it. So there's some sort of sophisticated linear algebra involved. And there are these things called central polynomials. And a central polynomial, and there's like in dimension n, there are central polynomials in dimension n. So there's different central polynomials for each dimension. A central polynomial is a polynomial in, non-commuting variables, I think 2n plus 1 variables, so that for every x1 through x2n plus 1, an element of the n by n matrices G of x1 through x2n plus 1 is in fact a scalar matrix. And of course, there's some non-zero value. They didn't even know these existed till the 1970s. And so, like for 2 by 2 matrices, you could take xy minus yx squared. Okay, and that is a central polynomial for 2 by 2 matrices. And the way to see that is, of course, you go back to the characteristic polynomial, remember, which is a squared minus trace a times a. And now this is not necessarily of determinant 1. Determinant times the identity equals 0. Well, notice, if the trace of a is 0, then a squared is the determinant of a times the identity. So xy minus yx, being a commutant, has trace 0. And squaring it, the characteristic polynomial says that this answer is the determinant of xy minus yx times the identity. And so the first of these were found by Ed Frohman, but then Razmuslov actually came up with the best ones. And now, given a ring like this, the Frohman center of the ring are all elements of the center that come from evaluating central polynomials. And to make it into an Amaya algebra, you invert any non-zero element of the Frohman center. And what this, it's just linear algebra. And there are some lecture notes from Michael Artin. He taught a course at Berkeley in like 1997, and Pavel Eddinghoff took the notes, and they're up on his webpage at MIT. And Artin gives a very, very coherent, exposition of the existence of these. And if you want, so what you do is you just invert an element of the Frohman center. What does this all have to do with skein algebras and the mapping class group? Okay, and this is Francis's idea of how to get invariance of elements in the mapping class group out of all this stuff. Okay. So theorem, and this is once again in this paper on Monday. if zeta is any root of unity, then zeta is any root of unity, then there is a Zariski open subset of the SL2C character variety. And here I better be careful. Zeta zeta had better not. So it's a root of unity, but to say it the way I'm saying it, the order of zeta is not divisible by 4. You have to avoid okay. There's a subset of the SL2C character variety that's variety of pi 1 of f, and now f has to be finite type. So that for every point in the open set, along with a choice of a root at each puncture, there exists a unique, irreducible representation of k zeta of f. Okay. So now this extra data doesn't really mean anything because it's peripheral and it's pretty stable and it doesn't move. What this means is if an element of the mapping class group fixes a point of the character variety, and that point is in this generic set, then that element of the mapping class group induces an automorphism of the representation, which means then you can write down a matrix. So what happens is mapping class phi plus fixed rep rho, what you get is a matrix. And that matrix is an invariant of the mapping class. That's where it all goes. So what'll happen in the next lecture, it'll be a lot less theoretical, okay? What I'm going to do is just restrict my attention to the torus where things are easy and write out the irreducible representations of the skein algebra, and then see how a particular mapping class acts in those representations and compute the matrix. Okay. A representation. Then what happens is in that representation, which is a homomorphism from the skein algebra to the matrices, the mapping class now induces an automorphism of the matrix algebra. But that automorphism of the matrix algebra comes from conjugation. And then you write down the matrix that conjugates, and that's the quantum hyperbolic invariant of that mapping class at that representation. And so quantum hyperbolic invariants were first defined by Baziak and Benedetti using a geometric quantization of the 6J symbols. And then Francis came up with this approach, and recently Baziak and Benedetti proved that Francis is getting the same answer as theirs. But Francis's motivation was Thurston's proof of the geometrization theorem for acylindrical manifolds, where you're taking advantage of the fact that there was a fixed point for the action of the mapping class group to come up with it. And so Francis's picture, it is intimately associated with the hyperbolic structure on the underlying manifold. That's the point of this viewpoint. There's another approach to this via Reshetikin and Koshayev that uses tangle functors. It's not clear how it's related to this. And finally, there's an approach of Hikami and Inui using cluster algebras, and that probably is the same thing as this. And this is quantum hyperbolic geometry that I'm talking about. Okay.
The next topic is for the
Well.